equation. Please, Elina.
Thank you very much for introduction. So the classical Euler-Poisson-Darboux equation is very well known, and it is defined by one of the form of this equation is given by the first formula. And here the interesting thing that in the left side of this equation we have Bessel operator, which is the main topic of my study. Such equation was considered in many papers, and as a model of random flights, it was presented in papers of Professor Arsinger, which you can see on the slide. Probably the first contribution in this area, the first who considered the random flights with such Euler-Poisson-Darboux equation was Sidney Goldstein in this paper on diffusion by discontinuous movements and the telegraph equation. And he considered the simplest random walk on the real line in which a particle placed at the origin at time 0 moves with 2 finite speed plus minus lambda, changing its current speed in accordance with the simplest Poisson process with a constant parameter mu. He discovered that the distribution of the position particle x during t is a solution to a telegraph equation of the following form. Here, if we take mu is equal to gamma divided to t, we obtain the equation with the Bessel operator. Next, such telegraph equation was considered by Mark Katz and Enza Arsinger in the following works. Natural generalization of this Poisson process when lambda is equal to lambda of t, and the generalization to the multidimensional case were considered in the following paper by De Giorgio and Professor Arsinger, Roberto Gara and Enza Arsinger, and also Yakus in statistical analysis of the inhomogeneous telegraphers process. We have also some papers in which were considered models of random walks with fractional derivatives. These papers of Metzler, Klafter, and Granflot, Vivaldi, and Mainardi. Also, in this work of De Giorgio and Enza Arsinger was considered such equation with Dirichlet displacement. So such equation defines the probabilic law in random walks on R, and we can consider also such equation with the fractional power of Bessel operator. The first such equation was presented in the paper of Roberto Gara and Enza Arsinger, random flights related to the Euler-Poisson-Darboux equations. But this equation wasn't solved in this paper, and next I will present the solution of this equation and also the attempt of simulation, the real random walk, and attempt to obtain such kind of equation and prove that this equation is really connected with random flights. So, from our point of view, if alpha is less than 1/2, the particle moves in average slowly, and when alpha is greater than 1/2 but less than 1, particle moves faster in average. The first we consider this equation when alpha is between 0 and 1/2. Now we can see this equation 4. This is so probably some kind of, for some beta it can be interpreted as heat equation, and for some beta it can be interpreted as wave equation. And the first one of the first paper where the solution of such equation was obtained, it was the paper of Gerasimov. This paper was connected to the mechanical problems, and later this equation was considered by Mainardi, and he called it fractional diffusion wave equation because for different kind of beta we obtain different kind of behavior of solution. Also, a lot of people considered such equation in the classical form, in the form of 4. For example, such equation were considered by Gernflo Mainardi, Professor Podlubny, and also we can find it in the famous book of Kilbas Srivastrava Trujillo, which is the book which were published in 2006 in the Elsevier. So, as we remember from my Friday talk, when we would like to introduce left-sided fractional Bessel integral on semi-axis, we can define it by this formula with the hypergeometric function, the kernel, by formula 5. If we would like to introduce left-sided Bessel fractional derivative on semi-axis, we would like to use computer approach. So we put iterated Bessel operator, and after that we take the integral operator. So when n is equal to natural number, it is just iterated Bessel operator instead of 6. As was mentioned in Friday, the fractional hyperbessel operators, which are more general than operators which I considered, this theory was very well developed by Professor Kyriakova and others. For example, in her book, Generalized Fractional Calculus, and in her paper with Professor Luchko, and in her separate paper, Breshkov integral transform and hyperbessel operators via G-function and fractional calculus approach. explicit solution and fundamental system of solution for fractional powers of hyper-Bessel operators, which are more general than my operators, was such results were obtained. But I consider next this equation 7, which is now not one-dimensional, but now we have the derivative by t, fractional power of Bessel operator, and the regular or just simple second derivative by x. And also here we have alpha from 0 and 1/2. It means that here we can put only one Cauchy condition in the form of 8. When t is equal to 0, it is just function f of x. Probably here t should be, of course, time, and x should be variable space variable. So I obtain the next theorem was obtained. If alpha is greater than 0 and less than 1/2, and lambda is greater than 0, and then we have the solution of problem 7-8 in this form. This is the generalized green function, has a form using this h function, which is quite difficult, of course, not very easy, but still here we can obtain this solution using regular methods, using integral transform methods. In more complicated case, when hyper-Bessel operator can be considered, I have no idea how we can obtain this solution in the exact as the exact formula, because the inversion in the general case is very complicated. But here it is possible. Each function is quite serious function. For example, it can be present as this Mellin-Barnes type integral, and in general case it can be presented as a series, only such this integral, but in some cases it can be written in some cases when for some b, beta, a, and alpha, it can be presented as a series. Here I would like to present only one only one series of conditions when this h function makes sense. In the literature, for example, in the book of Professor Kirakova or in the book of Kilbas and others connected to h transforms, we can find another cases when this h function makes sense. But here only one case is important for me, because I considered only h functions with such kind of parameters, and this case is important for me. This book, which I mentioned before, Theory of Applications of Fractional Differential Equations. In this book, we have the solution of the Cauchy problem with the computed derivative in the left side. And of course, I would like to take gamma is equal to 0 in my equation, and I would like to obtain the solution which was presented in this book in order to check if my solution is correct. So I have done it, and we can see that we obtain here psi function, and it is not very complicated to see that when we put gamma is equal to 0 in my solution, we obtain just psi function here, because we just have such formulas. So it was the first part in which the exact solution of the fractional differential equation, which is generalized Euler-Poisson-Darboux equation, was obtained. But my goal now is not just obtain the solutions of different kind of fractional equations. Actually, I would like to move to the application sphere, because it is now really interesting and important, not only study theoretical things, but also try to connect fractional calculus to the real world problems. And I decided to move to this sphere and to consider some generalizations, some approach to random walks. And I started from the beginning, as I think. Probably the first even not paper, but it was the first question which was presented by Crofton in mathematical question with their solutions from the educational times. It was a paper, not even journal, and the question was about traveler who was in the river and who could move forward and back randomly. And the question was how what is the distance he can what distance he can move, for which distance he can move for some time. Later in the nature, in the letter to Nature, Professor Pearson in the beginning of 20th century suggested the solution of this following problem. Actually, he suggested to find the probability that a man will be at the distance between r and r plus dr from the origin after n displacements if he started to move from a point 0 and walks 1 yard in a straight line. Then he turns through any angle, whatever, and walks another yard in the second straight line, etc. And the random walk problem has attracted the interest of many researchers. In particular, Lord Rayleigh answered that he solved this problem already 25 years before, but not in connected of the migration problem, because Carl Pearson considered the animal migration in connection to this problem, and Lord Rayleigh considered the sound wave spreading, and the model was the same. And here we can see the paper of Pearson and the book, you know, oh no, not book, the paper of Lord Rayleigh. Next, based on Lord Rayleigh conception, Kluwer proposed the general solution of random walk problem, and after that, Carl Pearson and his probably PhD student or assistant wrote a detailed study of problem of migration, and because it was in the beginning of the 20th century, they just didn't have a lot of instruments to do it, and most of their calculation were made by hand using series, just for series for Bessel functions. And here we can see two papers where such results can be found. Next, very famous book of Watson, A Treasure of the Theory of Bessel Function, and appeared. And in this book, we can find also multidimensional case of this problem. And the more detailed historical overview can be found in the papers of Dudka and Charder-Sekhar. It is really very interesting to see how this problem was developed, and what applications can be found according to this problem. As I mentioned before, Lord Rayleigh studied the problem of the theory of sound. And this problem was mathematically equivalent to the problem of the random walk. And Ronald Ross in this paper 2 presented a diffusion model of the random migration of mosquitoes. And he really studied the laws of spread of malaria. And all these applications were described by the similar models. Next, we can find in Pearson's paper migration problems, animal migration problems, and another application. It can be found in Wolkenstein papers, and this problem appeared as a description of polymer configurations. Next application of such random of Pearson random walks, we will call it Pearson random walks in order to just understand that we deal with the random walk when we can take any angle in each step, and we can find application in signals, in noise, in motion of microorganisms on surfaces, and in crystallography. And we can see such papers where such problems can be found. What is the new? Of course, all people who studied these random walks, they had a lot of things, but they probably didn't have a lot of instruments to deal with such models, and they consider only natural number which appeared as the indices of Bessel function, and they didn't notice that actually they deal with generalized translation. And I found that we can use our instruments which we developed for Bessel operator, and we can use it in this problem. And also we can simulate this problem and obtain that it is really works. So all my instruments I try to apply here. And now we turn to the quantitative model of random walks. So we consider agents A1, etc., AS, which are concentrated at the origin. So at the time t0, agent AI has a position x0. Then it starts to jump from the center, and at time t1, t2, etc., tn, it has displacement x1, x2, etc., xn. The resultant at tn time is Sn, it is a sum of such displacement. And the displacements are assumed to be independent, and the probability density of xm is pm of xm, and the probability density of Sn is required to be found. So we would like to find probability, and of course we can find, if we know probability, we can find probability density. We start from finding the probability in this form when Sn lies inside or on a circle of radius r. So I just would like to show the picture. We have some jumps here of different lengths, and here we have different angles, and finally we have the distance from the origin here, Sn. Here this is the distance of the origin, and if we put here a circle, we can find the probability that this Sn is all in this circle. So here we have the theorem. Let Lm denotes the length of the mth jump. M is from 1 to n, and we would like to find the probability that Sn is less or equal to r. So all agents are in the circle of radius r. And this probability is equal to this integral involves Bessel functions and the product of so-called normalized Bessel functions. Here we have the formula of this normalized Bessel function, and this normalized Bessel function is equal to 1 at 0, and that is why it's called normalized Bessel function. So this is the very nice formula 17. And actually, if we use real simulation in computer, so we have such agents and they jump and jump, they can do it weeks. And after that, we can obtain the result. And for some seconds, we can obtain the same result using this formula 17. In this theorem, for me, proof was very interesting. And I present here the proof. First, here we use this n-1 tuple integral of this form. And here we can see so the determinant which can be found when we use spherical coordinates. And in formula 18, the last or the first integral, which is presented here. Here we do not have limits in this integral. And here theta n-1 extend over the values such that Sn is less or equal to R. So, and in this step, we just can't to put here limits in this integration. But if we use Weber-Schaffer-Hetlin formula, probably very well known, probably not very well known, but it was presented in Watson's book, and also such formula was considered by Alexander von Stein. So if we use this formula, it is exactly what we needed, because here we have this non-zero value when S is from 0 and R, and when S is greater than R, we have 0. So this is just what we need here. And if we put it in our formula 18, we just obtain, we can obtain the limits of our integration. And we obtain this probably complicated formula, but we can just use next some techniques and obtain just one integral. So what we can notice here, we can notice then that we can use our normalized Bessel functions here, because actually we have such multipliers in our formula. Then we can see that we can calculate Sn using Sn-1 and Ln and angle theta n-1, because it is just the length of this segment. And we know how to calculate the length of this segment. It is just calculated by this formula. And this can be looked complicated, but it is very, very familiar for me, because it is our generalized shift, which is connected to the Bessel operator. And this shift, which can be written as t, acts to the normalized Bessel function as regular shift x to the exponential function. It is just generalization or another approach to, very well known algebra of exponential function. So here we can see this formula that our generalized shift acts to normalized Bessel function, and we can just obtain the product of the two normalized Bessel functions. And we have many integrals and we just in any step obtain this construction. And all our integrals just can be written as one integral of the product of the Bessel functions. This generalized translation first was introduced by Delsart as a solution of the equation with Bessel of the Cauchy problem to the equation for the Bessel operators. And next, Levitan developed a very huge theory of the generalized translation operators. This generalized translation connected to the Bessel operator was probably the most famous in this theory, because it is not very complicated, and we can generalize all harmonic analysis using this generalized translation instead of regular translation, regular shift. If we do it, we just obtain only one integral instead of n integrals. And here we can see it, and here we obtain the product of our Bessel functions. Next, if we just take a derivative of the Bessel function, we obtain the probability density, and it can be written as 22. Also, it is possible to calculate this integral even with this product of Bessel function. In the book of the Prudnikov-Brычkov-Marichev, this formula can be found, and it is a just Laurentiello function. So we can obtain the equation for this model, and we can do calculation. Probably it looks hard, and because it is, you know, unfold series complication, but if you will calculate it numerically, it is not extremely you know, extremely difficult, and it is just much more simpler than we use a real simulation. So here we can put, you know, the length of each jump is equal to L, and we obtain just power of normalized Bessel function. Next, if we do here very simple changing of variables, we obtain that here V is the speed of, you know, moving of our agents. It is very simple. And if nu is equal to 2, we obtain Pearson relay model, and also we can obtain here a Kluver model. And when nu is equal to k, we obtain Watson model. In the book of Watson, k was the dimension of the space, but in our work we consider also fractional real numbers of nu, and these numbers has different sense from it is, of course, if nu is equal to fractional number, to real number, not integer number, it is of course not the dimension of space. It is just the model with restriction to angle. And here I would like to stop. Thank you for your attention. And that's all. Thank you.
Thank you very much. Any questions, please? And I may not see hand raised, so just please unmute yourself and ask. No questions? Well, I will have then a question. In your first part, you talk of this Bessel operator on the left-hand side in some power. And on the right-hand side, you have always this second derivative, Laplacian. Can we also make fractional Laplacian on the right-hand side? I think it should not, from my point of view, should not be such a big deal, because on the left, you somehow have arbitrary power. So having arbitrary power on the left seems something like having power to be able to have a power on the right. So what can you say about this?
Yes, I started.
Second derivative, I put here fractional Laplacian.
Yes, we can study this model, and I actually had some results according to this model when we have fractional Laplacian from the right side of the 7. Yes, I have such results, but probably they are not very interesting because the techniques are the same, and I do not know does it have a really applicational sense. But of course we can do it. I think this case is the most has a lot of application, but I do not know, is it necessary here to consider the fractional power, but I can do it, yes.
Okay, then I possibly ask another question for the second part. The dimension, was it 2-dimensional working or 3-dimensional in your final part in this random walk discussion? Was 2-dimensional or 3-dimensional?
Yes, two-dimensional.
So all this, at the end, all these lengthy formulas with Bessel functions, they are all for 2-dimensional walks, yeah?
Yes.
And if we're looking at 3 dimensions, what will happen?
Yes, it is possible.
Also possible.
We just here will have not only theta but also another angle, and actually we did it with my husband and 3-dimensional random walk simulation also, but it is much more complicated to calculate. It takes if you have simulation, it takes very long time, and now we are waiting for the review to our paper, and if it will be positive and if it will be interesting to people, we can continue this topic and consider also multidimensional. You know, from the application point of view, only 2-dimensional and 3-dimensional case, I think, really interesting, because 4-dimensional it is just not what is it. So we considered this random walk in the space, but here I did not present it because we're just waiting for the result of our the reviewers.
Okay, thank you. Any other questions, please? So I just again remind you that I may not see hands, so just unmute yourself and ask, please, or somebody from the auditorium as well. No questions. Okay, then again, thank you very much, Elina, for a very nice talk.
Thank you very much.
Let me remind everybody that today we have 4 talks on our online seminar. So second one will be at 2 p.m. UK time, Professor Malchan. Therefore, thank you everybody for your attention, and then see you then.